Imagine a data center, a complex ecosystem where every server, cable, and cooling system plays a critical role. The challenge? Ensuring this environment operates efficiently without compromising performance or sustainability. High energy consumption, unpredictable maintenance needs, and the difficulty of real-time management create a perfect storm of inefficiencies. But there's more. Traditional methods often fall short, leading to increased operational costs and environmental impact. This is where the promise of virtual models comes into play, offering a transformative approach to these challenges. By creating a digital twin of the physical infrastructure, we can simulate, optimize, and predict with unprecedented accuracy. And here's why that matters. Virtual models allow us to monitor operations in real time, making informed decisions swiftly and effectively. Think about it, by analyzing temperature and humidity data, we can fine-tune cooling mechanisms to maintain optimal conditions while slashing energy use. This is not just a theoretical concept, it's a practical solution that's within our reach. And here's why that matters. Virtual models provide real-time monitoring and analysis of data center operations. Imagine having a digital twin of your entire infrastructure. This allows administrators to make informed decisions swiftly. For instance, by continuously analyzing temperature and humidity data, the system can dynamically adjust cooling mechanisms to maintain optimal conditions while minimizing energy use. This real-time insight is crucial for enhancing efficiency. Moreover, virtual models enable predictive maintenance, allowing data center managers to foresee equipment failures and schedule maintenance proactively, thus extending hardware lifespan and reducing operational disruptions. To start implementing virtual models, you need to configure the foundational elements. Begin by defining the scope of your virtual model. Identify the physical assets you want to represent digitally, such as servers, cooling systems, and power distribution units. Next, establish the communication protocols between your physical assets and the virtual model. Use standard protocols like Modbus or OPC UA for seamless integration. Ensure your sensors are correctly installed and calibrated. This is crucial for accurate data collection. Set up your automation software to interface with these sensors. For PLC programming, use a structured text or ladder logic to define the interactions between your physical assets and the virtual model. Remember, the accuracy of your virtual model depends on the precision of your initial configuration. Now, let's dive into the practical execution of virtual models. The core of this lies in the code logic and wiring within your programmable logic controllers, or PLCs. Start by defining your variables and data types. For instance, use int for integer values and real for floating point numbers. Next, establish your communication protocols. I recommend using Modbus for its simplicity and reliability. Set your baud rate to 19,200 and your data bits to 8. Ensure your stop bits are set to 1 and parity to none. For the PLC programming, utilize structured text or ladder logic depending on your comfort level. Remember, the key is to create a loop that continuously reads sensor data and adjusts actuators accordingly. If a sensor detects a temperature rise above 80 degrees Fahrenheit, your PLC should trigger a response, such as activating a cooling fan. This real-time adjustment is what makes virtual models so powerful. And here's a pro tip: always include error handling in your code. Use if statements to check for sensor failures or communication errors, and log these events for troubleshooting. This ensures your system remains robust and reliable. Now, let's dive into the advanced nuances and edge cases that can significantly impact the effectiveness of virtual models in data centers. One critical edge case involves the handling of transient states during equipment failure. When a component fails, the virtual model must quickly adapt to reroute operations and maintain stability. This requires setting up failover mechanisms in your PLC programming, ensuring that backup systems are activated within milliseconds. Another nuance is the optimization of cooling systems during peak load times. By fine-tuning the PID controllers, you can achieve a more responsive temperature regulation, reducing energy consumption without compromising equipment safety. Additionally, consider the integration of machine learning algorithms to predict load patterns and adjust resources dynamically. This proactive approach can lead to a 15% reduction in energy costs. Remember, the key to mastering these advanced techniques lies in continuous testing and iteration within your virtual environment. Now, let's dive into the common pitfalls you might encounter when working with virtual models in data centers. One frequent issue is the misalignment between the virtual model and the physical infrastructure. This can lead to inaccurate simulations and flawed decision-making. To avoid this, ensure regular updates to the virtual model to reflect any changes in the physical setup. Another pitfall is overlooking the importance of sensor calibration. Inaccurate sensor data can throw off your entire model. Regularly calibrate your sensors and verify their accuracy against known standards. Additionally, be wary of over-reliance on automation. While automation enhances efficiency, it's crucial to maintain manual oversight to catch anomalies that automated systems might miss. Lastly, when debugging, start by isolating the issue. Check the sensor data, PLC programming, and network connectivity one by one. Use logging to trace the flow of data and identify where it deviates from expected behavior. Remember, a well-maintained virtual model is your best tool for enhancing data center efficiency and sustainability.